This is your presenter, Asloob Mudassar, and I am presenting slide number 15C of the course on atomic and molecular physics. In the today's lecture, I shall be covering LS coupling and application of LS coupling will be used in the study of the first two excited states of the atomic nitrogen. This is the third lecture of the series entitled with many electron atoms. So this is the third lecture of the series of many electron atoms. In the previous lecture, I have presented the ground state configuration of the atomic nitrogen using symmetry arguments and using microstate tables. There we studied the ground states of the nitrogen in much greater detail. And in the today's lecture, I shall be purely studying the first two excited states of the nitrogen using the LS coupling technique. Terms of the ground states of the nitrogen in full. Sorry, this is the lecture that I have covered. Now, in the today's lecture, I shall be starting from the terms in the excited states of nitrogen. You see that the ground state of the nitrogen was 2p3. So when one of the electron is moved to the 3s state, then the first excited state becomes 2p2 and 3s. This is the first excited states of the atomic nitrogen. The two electrons in 2p2 are equivalent. That is, we cannot discriminate between the two electrons in the 2p2 subshell. Based on the Pauli exclusion principle, they form the following terms. So you see that first of all, I shall be studying the two electrons in the 2p square orbit, that is in the 2p2, and then after studying those, I shall find out the total angular momentum and the total quantum number, orbital quantum number and the spin quantum number, and then I shall use these quantities along with the orbital quantum number of the 3s electron, and the spin of the 3s electron will be combined with the resultant values obtained from 2p2, and then of course the resultant excited the terms in the resultant excited states, first excited states of the nitrogen will be found. So for 2p2, I have L1 is equal to 1, L2 is equal to 1, because the value of orbital quantum number for both 2p electrons is L is equal to 1 and L is equal to 2. Sorry, L2 is equal to 1, L1 is equal to 1, L2 is equal to 1. So let's combine them. The total value of the orbital quantum number capital L is equal to mod of L1 plus minus L2, and putting the values of these values, mod of 1 plus minus 1 will give you 2 comma 1 comma 0. When you add them, you will get 2. When you subtract them, you will get 0, and you need to put all the other values in between 2 and 0, which is 1. And the term symbols associated with the orbital quantum number 2, 1 and 0 are respectively D state, D symbol, P symbol and S symbol. S corresponds to L is equal to 0, P corresponds to L is equal to 1, and D corresponds to L is equal to 2. Now let's talk about the addition of their spin quantum numbers. So here I am assuming that the two electrons are in the same spin category. For example, now the one of the electron is in the, you see that I am going to study 2p2. So in the 2p2, it is possible, it is possible that the two electrons are in the separate sub shells of the p orbital. Then they have the parallel spins, and for that one I can write the mod of s1 plus s2 is equal to mod of half plus half. I have used the value of a plus sign over here because I am assuming here that the both spins are parallel to each other, that is they are parallel, and that is why I am using plus sign over here, and the total value becomes equal to 1. And the multiplicity, corresponding multiplicity is given by m1 is equal to 2s plus 1, and the value of here capital S is equal to 1 over here. So putting that value over here, the multiplicity becomes equal to 3. So when the two electrons are in the parallel state, the corresponding multiplicity will be equal to 3. Now I am assuming that the two electrons are in the anti-parallel states. So I have the mode of S1 plus minus S2, which will be equal to half minus half. This negative sign indicates that the spins are anti-parallel to each other, and you see that their addition is equal to 0. So capital S is equal to 0 over here, and the multiplicity, which is equal to M2, we are regarding it as M2. M2 is equal to 2S plus 1, and putting the value of S is equal to 0 over here, the multiplicity of this state becomes equal to 1. So now we have two multiplicities. M1 is equal to 3 and M2 is equal to 1, provided in the two cases corresponding to the two electrons have the same spin and the two electrons are in opposite spin. Okay, and you see that when I added the orbital quantum numbers, L1 is equal to 1, L2 is equal to 2, I obtained the total quantum number, orbital quantum number is equal to 210, and with the corresponding term symbols capital D, capital P, and capital S respectively. For the D and S terms, you see that D and S terms are directly obtained by the addition and by the subtraction. That's L1 plus L2. When they are aligned with each other, that is L1 and L2 have the same direction, we get 2 over here. But when L1 and L2 are oppositely directed, we get 0 over here. So what about 1? 1 can be obtained when L1 and L2 are non-parallel. That is neither parallel nor anti-parallel. And in that case, we are using that the multiplicity. So let me read this paragraph first. For the D and S terms, the angular momenta L1 and L2 are adding parallel and anti-parallel respectively. That is, when they are parallel, you get 2. When they are anti-parallel, you will get 0. Corresponding terms are D and S. And the corresponding spins will be anti-parallel, and the multiplicity M2 will be equal to 0. So you see that when D and P, which are directly obtained when L1 and L2 are parallel and anti-parallel respectively, in that case, the multiplicity will be used when the electrons have anti-parallel spins. So we have M2 is equal to 1. Thus, the terms with the correct multiplicities are 1s and 1d. So you see that now up to this point I have only the term symbols d, p, and s. Now using these arguments given in this paragraph, I have used the multiplicities along with that one, and now the term with the multiplicities are 1s and 1d, where 1 stands for the multiplicity which is obtained from M2 is equal to 1 when the two electrons have anti-parallel spins. And we used these anti-parallel spins only when the orbital angular momentums were parallel or anti-parallel to each other. So when they are parallel, you are getting L1 plus L2, which is equal to 2. When they are anti-parallel, you are getting L1 minus L2, which is equal to 0. So in these two cases, we are using the spins which are anti-parallel to each other, and we obtained the corresponding multiplicity 1. So I am using the multiplicity 1 along with these two S and P terms. So I have 1s and 1d. These are the terms along with the multiplicities. For the P term, you see that the P term was obtained when the orbital quantum numbers L1, orbital angular momenta L1 and L2 were not parallel or anti-parallel. So they are making different directions. In that case, the addition will result in the form of P terms. So for the P terms, the angular momenta L1 and L2 are adding neither parallel nor anti-parallel, and the corresponding spins will be parallel with the multiplicity M1 is equal to 3. So the terms with the correct multiplicity is 3P. So you see that now I have used in the multiplicity 3 over here. The reason is what I have explained, that since L1 and L2 are not parallel to each other, in order to obtain the value of 1, and on the other hand, we are using the case when the two electrons have parallel spins. So in that case, the multiplicity is equal to 3. So I am using the multiplicity C with only the term P. So now the term becomes 3P. So you see that now I have labeled the terms with the multiplicities. So I have the terms with the multiplicities 3P and 1S and 1D. And the corresponding value of capital S. Let us combine the core angular momenta, the angular momenta, that is the orbital angular momenta, and the spin angular momenta obtained using these terms will be referred to as the core angular momenta, and the core angular momenta will be referred to as LC and SC. LC stands for the core orbital angular momentum and SC stands for the core spin angular momenta. So I shall be combining these angular momenta with the angular momentum of the 3s electron, which is designated as L is equal to 0 and S is equal to half. L is equal to 0 for the S term, and S is equal to half is actually the spin quantum number of the one electron that is contained in the 3s orbital. So you see that Lc and Sc will now be combined with L and S of the 3s electron, and Lc and Sc will be obtained respectively from the 3p, from the 1s, from the 1 and from 1d individually, which is explained in the next on the next page. So you see that now we are going to couple the core values of angular orbital angular momenta and the spin angular momenta with the 3s electron. So let us combine the core angular momenta Lc and L and Sc with the angular momentum of the 3s electron. And for the 3s electron, I have L is equal to 0 and S is equal to half. So the resulting L, that is the resulting L after coupling of the core momenta of the core angular momenta with the 3s electron will result in the value of capital L and in the value of capital S. So I am referring to them as resulting capital L and resulting capital S. The resulting capital L will be obtained by LC plus minus L, and the resulting S will be obtained by SC plus minus S. So let's study the 3P state. The 3P state that I have obtained by from the 2P2 state. So you see that these three states, 3P, 1S and 1D, you know that were obtained when I analyzed the 2P2 state. And now I am combining the terms obtained from 2P2 state with the 3s electron. So that's why I have the headings coupling with the 3s electron. Now you see that for 3P, the formula that I shall be using, I shall be using these two formulas, that is capital L is equal to LC plus minus L and capital S is equal to SC plus minus S. Capital SC and capital SC will be obtained from 3P. So from the 3P, since the multiplicity is 3, the value of the capital S is equal to 1 that I have used over here. And since the symbol is P, the value of the capital LC is equal to 1 because of the symbol is P. And this 0 value is what I have obtained from L is equal to 0, and I have also obtained S is equal to half. So I am using this value 0 over here from the 3s electron and 1/2 value from the spin quantum number of the 3s electron. So you see that this L is equal to now 1 plus minus 0 will give you 1, and S is equal to 1 plus minus half will give you 3/2 and 1/2. Now since L is equal to 1, the states will be referred to as, or the term symbols that I shall use will be capital P, and the capital S is equal to 3/2 and 1/2, and the corresponding multiplicities will be equal to 4 and 2. So I have used 4P and 2P as the multiplicities with these two states. And you know that the multiplicity is given by 2 times capital S plus 1, and the capital S values are 3/2 and 1/2. So using these two values, I have obtained the multiplicities equal to 4 and 2, and I have used two multiplicities over here. So for the 3P, when I used the 3p terms from the 2p2 electrons, and when it is combined with the 3s electrons, I obtained 2p. I obtained these two terms. One term is 4p and the other term is 2p. Now let's combine the 3s electron with the 1d term obtained from the 2p2 state. So for this 1D, the value of the value of LC from this capital T is equal to 2. And from multiplicity 1, the value of capital S is equal to 0. So I have used 0 over here. And these two values which are indicated in the red are obtained from the 3s electron, which is L is equal to 0 and S is equal to half. So using L is equal to 0 and S is equal to half along with these two, I have obtained the value of 1D as half. Sorry, I have obtained capital L by combining 1D with the 3s electron. I have obtained capital L is equal to 2 and I have obtained capital S is equal to 1 half. So capital L is equal to 2 means that we are talking about the D term, and this 1 half capital S is equal to 1 half means that the multiplicity is 2. So I have used 2 as the multiplicity with the term D. So by combining 1D obtained from the 2p2 state with the 3s electron, I have obtained the corresponding term with multiplicity as 2d. Now the last term is 1s, because you see that previously I obtained these three terms 3p, 1s and 1d. I have presented the combination of 3p state with the 3s electron, and also the combining the combination of 1d with the 3s electron. Now I am going to combine 1s term symbol with the 3s electron. So this is given over here. For 1s electron, I have capital L is equal to 0 plus minus 0. And you know that capital S is equal to 0 over here. From capital S, I obtained capital LC is equal to 0. And from the multiplicity, which is equal to 1, I obtained capital S is equal to 0. So, and these values in the red are obtained from the 3s electron with L is equal to 0 and S is equal to half. So obtaining these one, I obtained the value of capital L is equal to 0 and the corresponding symbol is capital S, and I have obtained capital S is equal to 1 half and the corresponding multiplicity is 2. So the term 1s when combined with the 3s electron will give you the term as 2s. So I have obtained now four terms for the 3s electrons, and these four terms are 4p, 2p, 2d and 2s. These are the four terms, final four terms that I have obtained. When I have come, these are the four total terms that I have obtained from the ground, from the first excited states of the nitrogen atom, and that first excited state is 2p2 and 3s. First of all, I obtained the terms using 2p2, then I combined their angular momenta with the angular momenta of the 3s electrons, and then I obtained the final terms, and those are 4 in numbers, which are shown with the multiplicities over here 4p, 2p, 2d, and 2s. Now you see that I am using the Hund's rule in order to arrange these four terms in terms of energy. So 4p being highest multiplicity has the lowest energy, then the 2p term, because I have to arrange these two p2 terms, because these two terms, that is the 4p term and the 2p term, were obtained from the 3p, and 3p has the highest multiplicity. So the arrangement of energy will be given according to these terms. So you see that out of these three terms, the 3p term being the highest in multiplicity will have the lowest energy. So all the terms that I have obtained using the 3p terms will have the lowest energy. And you know that when I used the 3p term, I use only the two terms, that is the 4p and the 2p. And since 3p term over here in this category has the maximum multiplicity, means lower in energy. So I am going to use this 4p and 2p to have the lowest energy. And out of these two, that's the out of the 4p and the 2p, the 4p being highest in multiplicity will have the lowest energy. So the next energy term is the 2p. Now I am left with two other terms. So once I have arranged the terms obtained from 3p, then the two terms are 1s and 1d. And you know that 1s and 1d have the same multiplicity, which is equal to 1. So when the multiplicity is the same, the second Hund's rule states that the highest value of L will have the lowest energy. So D has the value of L is equal to 2, so it has the lowest energy in comparison with 1s. So I am going to, and you know that when I used 1d with the 3s electron, this 1d was converted into 2d. So I am arranging this 2d as the next lowest energy term. And now when the final term is 1s and the corresponding energy term is 2s, so I have used 2s. So you see that I have arranged the term in the lowest to highest energy terms from left to right. Then so energy wise distribution is 4p, 2p, 2d and 2s. And you know that these two terms, that is the 4p and the 2p terms, were obtained when the term 3p was combined with the 3s, with the orbital angular momentum of the 3s electrons. Since this 3p has the highest energy, so all the corresponding terms which correspond to 3p, which were obtained using 3p, will have the lowest energy. So 4p and 2p has the lowest energy, and out of these two terms, the 4p has the lowest value in energy. So I have arranged the 4p and 2p, and these two terms, that is the 2d term and the 2s terms, were originated by from the term 1d and 1s when these two terms combined with the orbital when these two terms combined with the angular momentum of the 3s electrons. So 1d, from the 1d we obtained 2d, from the 1s we obtained 2s. So 1d, since has the for the 1d and 1s the multiplicities are the same, the lowest value of d is equal to capital L is equal to 2. So I have used the corresponding term as the 2d term, and then the 2s terms were arranged as the highest term. So this is what I have arranged the terms obtained from the first excited states of the atomic nitrogen, and these terms have been arranged along with their multiplicities. Now you see that now I am going to arrange these terms with the value of the total angular momentum J of the atom. So full term of the energy wise distribution of the first excited state 2p2 and 3s. This was the first excited state, and now I am writing the full term. That is, I am writing the value of a total angular momentum J of the atom and the principal quantum number along with these states. You know that these states were obtained by the contribution of the 3s electron. So this 3 will be used as the principal quantum number along each of these terms. And you know that I have used 3 as the principal quantum number along each of these terms. And now I am writing down the total quantum number J. How to write the total quantum number J? The total quantum number J is actually the mod value of capital L plus minus capital S. The capital L obtained from the term P is equal to 1, and the capital S obtained from the term 4 is equal to 3 by 2. So I am combining total angular momentum. I am obtaining total angular momentum J, that will be equal to mod of 1 plus minus 3 by 2. And I shall obtain these value 1 half, 3 half, and 5 half. And now from this term, which is the p term, the value of capital L is equal to 1 for this p term, and the multiplicity is 2. The value of capital S is equal to half. So to obtain the total value J of the total angular momentum, I am combining 1 plus minus half. So the total values of angular momentum J of the atom will be equal to half and 3 half. And then the third term is D. For the D, the value of capital L is equal to 2. The multiplicity is 2. The value of capital S is equal to half. So I am adding 2 plus minus half mod. That will give you the two values 3 by 2 and 5 by 2 as the total values of the total values of the angular momentum J of the atom. So for this state, the term is capital S. The value of capital L is equal to 0. The multiplicity is 2, that is capital S is equal to half. So I am adding 0 plus minus half, which will give you half value. So the total angular momentum J is half. So you see that now I have written the value of the total angular momentum J of the atom along with each term. And you see that the lowest value of capital J, the lowest value. So you see that the lowest value of angular momentum is written first, that is 1 half. Then the highest value of J according to energy wise is 3 half. Then the next value of the energy term according to the value of J is 5 half. So the term with the P 1 half is lowest in energy out of these 4P terms. Then the term with 4P 3 half will be the next higher energy term, and then the 4P 5 half will be the next higher energy term. Similarly, I have obtained these values of the total angular momentum energies, and I have arranged them energy wise. That is, the total angular momentum J has also been arranged according to energy wise. The lowest energy of J will be lower, the lower value of J will have the lower energy, and the higher value of J will have the higher energy. Now you see that I have specified E symbol over here with each state. That is, I have written superscript E with each term, and this E stands, that is, the term has the parity equal to even. So the even parity. So all these terms are even parity terms. And you know that to obtain the parity of a term, you have to add up the values of the orbital quantum numbers. So these orbital quantum numbers will give you the even values. So I have obtained that these are the even parity notations have been used along with each terms, and these the parity calculation have been explained in the previous lectures. So you see that I have arranged all these terms which were obtained from the first excited states of the atomic nitrogen as in the energy distribution from the left to right. The term in the lowest in the left on the left are the lowest in energy, and the terms on the right are the highest in energy. So these are even parity terms, and their transitions to the odd parity term of the ground state are much stronger. You know that the ground state terms have even parity, whereas the first excited states have the ground state term of the atomic nitrogen. All those terms were having odd parity, and the first excited states of the atomic nitrogen, as we see, that has the even parity. All these states have even parities. So the transition from the even parities to the odd parities are much stronger. Same parity transitions are usually forbidden or weaker. And you know that the transitions from the first excited state to the ground states of the nitrogen being opposite in parity will have the strongest transitions. And the selection rules that will be used are delta S is equal to 0. Delta S is equal to 0 mean that the transitions will take place between the two states which will have the same multiplicity. So delta S is equal to 0 means that the transition will only occur between the states having the same multiplicity. Either multiplicity of the two states are 4 and 4, or the multiplicity of the two states is 2 and 2. Delta L is equal to 0 plus minus 1. That is the angular, that is the change in orbital quantum number should be equal to 0 and plus minus 1. And the change in the total values of the quantum number J should be equal to 0 plus minus 1. But from 0 to 0 transition is forbidden. However, that for example, if j is equal to for the higher state, if j is equal to 3 by 2, and the lower state for the lower state the j is also 3 by 2, then 3 by 2 minus 3 by 2 will be equal to 0. That's fine. But if the higher state has j is equal to 0 and the lower state has j is equal to 0 also, then the transition from j is equal to 0 to j is equal to 0 is not allowed and is forbidden. And the even to odd parity transitions are preferred. They are stronger transitions, and these are the optically aroused transitions from even parity to odd parity, or from the odd parity to the even parity. So this is what I have explained the first excited states of the nitrogen. Now I am going to explain the second excited states of the nitrogen. The terms in the excited states of the nitrogen. The second state of the nitrogen is 2p2 and 3p. That is, in the first state, the first excited state, the electron was the 3s electron, and now by providing the energy to the 3s electron, I have moved the 3s electron to the 3p electron. So the next excited state is 2p2 and 3p. And you see that we have obtained in the previous you see that description about the first excited state. I have obtained the term symbols corresponding to 2p2 by applying the ls coupling, and then the resultant values of the orbital quantum number L, orbital angular momentum Lc, and the spin quantum number Sc were combined with the 3s electron in the previous, and now we shall combine them with the angular momenta of the 3p electrons to obtain the final terms. So the two electrons in the 2p2 are equivalent. Based on the Pauli exclusion principle, they form the following terms. So L1 is equal to 1, L2 is equal to 1 for each of these 2p electrons. So capital L will be equal to L1 plus minus half mod, which is equal to mod of 1 plus minus 1, and these two values will be equal to 1, 0, and the term symbols will be equal to D, P, and S. These are the same terms as we have obtained for the case of the first excited state. So you see that again this is the same analysis for the case of first as the same as for the case of first excited state. That is when the two spins are parallel to each other, we have m1 multiplicity is equal to 3, and when the two states have when the two electrons have opposite spins, then of course the multiplicity will be equal to 1. And this is only the case for the p term. And this is the case both for the d term and the s term, as we have explained before. So these two paragraphs are actually the same things which were obtained, which were relevant to the 3s electron. So these same are also relevant to the 3p electron. That is relevant to the second excited states of second excited states. And you know that we have the d term and the s terms, and then you see that we have the total multiplicity is equal to 1. In this case, this is what I have explained in the previous few pages, and then the terms that will have along with their multiplicities is the 1s term and the 1d term, and the p term which will correspond to the value of term. You see that I have written these terms, that this p term will have, for this p terms we should have the multiplicities in the parallel, and you see that in that case I have multiplicity 3, multiplicity is equal to 3, which will be written with the term p, and then I have the final term is 3p. So the terms corresponding the term corresponding to the core electrons for the second excited state, and the core electrons were 2p2 electrons, that is the 2 electrons 2p electron. From these 2p2 electrons, I have obtained these terms, that is 3p, 1s, and 1d terms. Now I shall combine the angular momentum, I shall combine the angular momenta of these terms with the angular momenta of the 3s electron to obtain the final terms. So let's perform the coupling with the 3p electrons. So let's combine the core angular momenta LC, SC, which were obtained from 3p, 1s, and 1d individually, or separately. So these LC and SC values will be obtained from 3P, 1S and 1D. So let's combine the core angular momenta LC/SC with the angular momentum of the 3p electron. And for this 3p electron, the value of L is equal to 1 and the value of P is equal to half. And when I shall combine the angular momenta LC/SC with the angular momentum of the 3p electron, the resulting value of orbital angular momentum L and the spin angular momentum L will be given by this relationship. And here I am writing the total. This L will stand at the total value of the orbital quantum number, and this S will stand as the total value of the spin quantum number. So let's obtain these two values for the value of 3p state. So for this 3p state, the value of LC is equal to 1 and the value of SC obtained from the multiplicity 3 is equal to 1. And for the 3p electron, I have L comma S is equal to 1.5. So 1 is written in bold, which corresponds to value of L for the 3p electron, and half is the value of the spin angular momentum for the S electron. So for the 3p electron, I have capital L is equal to 1 plus minus 1. So you see that this red one in the red is from the LC, and this one in the bold is from the value of the 3s electron, which is 1. So combining these two values, I shall obtain 2, 1, 0. These three values will be obtained, and the terms will be designated as D, P, and S respectively. And the capital S values will be obtained from the SC plus S, and the SC value is equal to 1 shown in green, and the value of S for the 3p electron is equal to half, which is shown in red. And combining these two, you obtained two values of the spin quantum number, which are 3 by 2 and 1/2. So I have these term symbols D, P, S, and the values of the spin quantum number, total spin quantum numbers are 3 by 2 and 1/2. So I shall be combining these with the multiplicities obtained from this value of capital S, and the terms can be written as shown below. So the terms will be so these are the terms you see for the 3p. So I have, when I coupled the 3p electrons, that is when I coupled the 3p angular momenta of the 3p term with that of the 3p electron, I obtained these terms, these three terms, D, P, and S term, these three term symbols, along with the total value of capital S is equal to 0, which corresponds to the multiplicity 3 by 2 corresponds to the multiplicity equal to 4, and 1/2 corresponds to the multiplicity is equal to half, multiplicity equal to 2. So now I am writing down the multiplicities with these terms. So with the D terms, I shall write two multiplicities, 4 and 2. And with each of these terms, I shall write the two multiplicity values. One is 4, the other is 2. So you see that with these terms, some of the terms have multiplicities 4, and some of the terms will have the multiplicities equal to 2. Okay. So you see that you can obtain, I have used O with each of these terms. O means that these terms have odd parity. And you see that I have also written the values of the total quantum number J of the atom. And it is very easy to obtain the value of total angular momentum J of the atom. The total value of J is obtained by combining the total value of capital L plus minus capital S. And you know that from each term too, you can obtain the value of capital S, capital L, and capital S. For example, this is the S term. The capital value of the value of capital L is equal to 0 for S term, and from the multiplicity to the capital value, the value of capital S from this multiplicity to is equal to half. So the total value of J, capital J, is equal to L plus minus S, that is a mod of 0 plus minus half, which is equal to half. Similarly, let me explain, for example, the value of the value of the total angular momenta I have written for these 4D terms. For the D term, I have capital L is equal to 2. From the multiplicity 4, I have the capital value, I have the capital S is equal to 3 by 2. So I have capital L is equal to 2 and capital S is equal to 3 by 2. And the total value of capital G is equal to mod of capital L plus minus capital S, that is the mod of 2 plus minus 3 by 2. So if you evaluate the mod of 2 plus minus 3 by 2, you will obtain these terms: 1 half, 3 half, 5 half, and 7 half. Similarly, the values of the other quantum number, other total angular momentum of the quantum numbers will be obtained. Now the question number is that I have now can you arrange them as energy wise? These have not been arranged as energy wise. That is, I have randomly placed them. But you can also arrange using you can also arrange it according energy wise using Hund's two rules. That is, the highest multiplicity term with the will have the lowest energy. So for example, out of these terms, this 4D term, this 4 has the highest, that is 4s. This term has the highest multiplicity. Then 4p term also has the highest energy. Then for example, the lowest energy. Then the multiplicity 4 has the lowest energy. So when all these three terms have multiplicities equal to 4, that is 4s, 4p, and 4d terms. These have the highest multiplicities. When the multiplicities of some terms are equal, then we look for the values of capital L. The terms with capital L has the highest value of the capital L will have the lowest energy. So it means that 4D term will have the lowest energy among all these by applying the Hund's rule. Similarly, you can apply the Hund's rule to the other terms and you can distribute them energy wise. And the Hund's rule is what I have discussed in one of the previous lectures. Now let's combine the angular momenta obtained from the 1D term with the 3p electron. So from this 1D term, I have capital C is equal to 2. And from the multiplicity 1, I have capital CSC is equal to 0. And from the 3p electron, I have L and S respectively 1 comma half, shown in bold and red. And then you see that the total value of capital L is equal to 2 plus minus 1. 2 is in the red from LC and 1 from the 3p electron. So 2 plus minus 1 will give you 3 to 1. Similarly, and the corresponding term states will be F, D, and P. And this capital S is equal to 0 plus minus half. And when you combine 0 plus minus half, you will get half value over here. So you can also evaluate the total value of the total angular momentum J from using the value of capital L from this P term, which is equal to capital L is equal to 1, and from the multiplicity capital S is equal to half. Then you have 1 plus minus half, which will give you 1 half and 3 half as the values of the total angular momentum J of the atom. Similarly, you have P term, D term, and F term, and the multiplicity is 2. Multiplicity will be equal to 2 for all these three terms which I have written, and I have also written the value of the total angular momentum J of the atom. Now you see that let's move to the 1s term. So when you combine the total angular momenta of the 1s term with the angular momenta of the 3p electron, you will obtain these terms. that is the total capital L is equal to 1, which stands for the P term, and the total value of capital S will be equal to half, which will stand as the multiplicity equal to 2. So the term will be equal to 2 P naught, and I have also written the value of the total quantum number J of the atom. And O means that these terms have odd parity. And the method of calculation of the parities is what I have given in one of the previous lectures. Now let's write full form of energy-wise distribution of the second excited state, which was 2p2 and 3p. So I have obtained many terms for this one, and these terms have been shown. For example, these are many terms. Then of course these are the terms, and then of course this is the final term. So we have obtained many terms from them, and now it is the time to combine them or arrange them in energy-wise distribution. So first of all, I shall write down the terms obtained using 3p, because this 3p has the highest multiplicity. So first of all, I shall arrange their terms first, and their terms are what written over here. And these terms in energy-wise distribution will be written over here. For example, this 4p, then 4s, then the 2d, then 2d, then 2s. And I have missed which term I have missed over here. So let me look over here. So where is the 4d term and 4p term? Okay. So you see that I have the 4p term over here, then I have the 4s term over here, then 2d term, then 2p term, then 2s term. So full term energy wise distribution of second excited state. So actually I have obtained, you see that many terms I have obtained over here. These are the terms that I have obtained. And I have to arrange these terms over here. So these terms, you see that have, where is the 4D term? So I think that I am making some mistake over here. That is the terms have not been arranged properly. So in the next lecture, I shall continue my lecture from this onward to complete the lecture, because there are some incorrect values over here and I have to correct them, because my total terms are these are the terms and I have to correct these terms over here. And after correcting them, I shall continue my lecture from here. So I am going to end my lecture over here because there are some incorrect values over here. So after correcting my lecture, I shall continue the next lecture from this onward. So for the time being, I can say that this is the end of lecture number 15C, and the lecture is continued.